Hey everyone, and welcome to this video on graphing quadratic equations and functions. I hope you enjoy. Alright, so we've already graphed a whole bunch of equations and a whole bunch of functions, but so far they've all been lines. And there are so many other types of equations and functions that we can graph, so I'd like us to explore just a few more of them. So in this first example, we've got y equals x squared. And this is an incredibly important function, and one that we need to become really familiar with. In this case, since our equation is already in y equals form, our strategy is going to remain exactly the same. Because there are two variables in this equation, there are going to be infinitely many ordered pairs that work with it. And we couldn't hope to ever list them all or graph them all. So we're going to find a collection of ordered pairs, graph them, and hopefully they create some sort of pattern that we can then extrapolate from and draw a graph representing all of the ordered pairs for this equation. Again, we want to be systematic with what inputs we use, usually starting with 0, using positive inputs and negative inputs, and using a wide range of them to get the best picture of the graph we can. So why don't we go from -4 to +4? Why don't you find those ordered pairs, graph them, and then let's reconvene and see what we're looking at. Now it seems like we've really exhausted all of our usable inputs, because if we put in an x value that's any greater than 4 or any less than -4, we're just going to get greater and greater outputs that are not going to fit on our graph. So let's see what we've got. Looks like we've got this sort of U-shaped sort of graph. Now we'd love to connect these dots and draw that U and extrapolate and say that this pattern goes on forever and ever, but we've really only found a few ordered pairs. We didn't do any decimals, we didn't do any fractions. We could try some more numbers, but hopefully this pattern will continue. But in order to make sure, let's use a little graphing calculator piece of software for the computer to make sure. Alright, what we've got here in the upper right are the inputs and outputs for the function y equals x squared. And what I'm going to do is I'm going to switch up what the input is, and we're going to see what the outputs are, and this graphing calculator is going to sketch that graph as we go. So you see, we're doing a whole bunch of inputs and outputs here, way more than we could ever do by hand, and we see that the graph that's created is exactly the kind of U-shape that we did by hand. So, of course, there are these infinitely many ordered pairs, and it wouldn't make sense to do them all by hand, but it's great to see that the graph we created with just a few ordered pairs was good enough to accurately figure out what this graph is supposed to look like. Alright, back to our hand sketch graph. Well, now that we know what this is supposed to look like, and we confirm that we did a great job the first time around, let's go ahead and connect our points and make our graph. Remember that we expect this pattern to continue in this way, so we're going to add these arrows so that we can adequately say that we have captured all of the ordered pairs that make this statement true. In this case, since the graph goes through the point 0, 0, the origin, it happens to be that our y-intercept is 0 and our x-intercept is 0, and they happen to be the exact same point. That's going to be the case only when our graph goes right through the origin. One thing that's really nice about this graph is it appears to be symmetric. If we were to draw a line right down the y-axis where x equals 0, our graph would be a mirror image of itself. Now, why might that be the case? Well, if you square a number or its additive inverse, you arrive at the same thing. For instance, 2 squared is 4 and -2 squared is 4. 3 squared is 9 and -3 squared is 9. So, kind of makes sense that we might end up with this symmetric graph. Now, I'll tell you now that a lot of the graphs we're going to draw right now are going to be the exact same shape as this graph right here. It's actually called a parabola, just moved around left, right, up, or down, or something of that variety. So it's really helpful to know this graph inside and out. Alright, let's try another one. Alright, let's graph all the ordered pairs for y plus 4 equals x squared. Now note, the only difference between this one and what we did last time is that the y has been replaced by a y plus 4. Now, before we go ahead and create some ordered pairs, it's probably going to be a good idea to rewrite this in y equals form. Alright, now that we have it in this form, why don't you pause the video, please find some ordered pairs for this graph, graph those ordered pairs, and let's see what happens. Again, I would start with 0 as your first input, then branch out in either direction from there, both positive and negative, to find ordered pairs. All right, once again, we got one of these U-shaped or parabola-shaped graphs. A couple of things to note. Our y-intercept in this case is right at the very bottom of this U at the point 0, -4. And it appears that we have two x-intercepts because this graph hits the axis 2 times, both at the point 2, 0 and at the point -2, 0. Note that once again, it appears that this graph is symmetric about the y-axis, and it has the exact same shape as the graph we had before, y equals x squared, but this parabola, this u, appears to be exactly 4 units lower than the other one. And I'd like to use that graphing calculator app again to show you that that's exactly what happened. Alright, what we've got now is a red graph and a blue graph directly on top of each other, even if the blue graph is hard to see. And the blue graph is the graph of y equals x squared, and the red graph is currently the exact same thing because it's y plus 0 equals x squared. But let's see what happens when we take this 0 and we change it into a 4. We see that changing the y, or replacing y with y plus some number, in this case y plus 4, had exactly the effect that we found when we graphed it by hand. It moved our graph down 4 units. Alright, let's try another one. Let's graph all the ordered pairs for y minus 2 equals x squared. Of course, compared to our original graph, y equals x squared, all we've done is replace the y with the y minus 2. Before we find the ordered pairs, let's go ahead and put this into y equals form. We end up with y equals x squared plus 2. So, on your own, why don't you please find the ordered pairs for this graph, graph those ordered pairs, connect them if you find a pattern, find the x-intercepts and y-intercepts, and then we'll reconvene to talk about it. Again, I suggest you start with an x value of 0, and then branch out to positive and negative x values surrounding 0 in order to piece together this graph. So one thing that we notice right off the bat is that this graph does not have any x-intercepts. The graph never happens to cross the x-axis ever, and that's totally fine. We still do have a y-intercept. Again, that y-intercept is at the very bottom of our parabola, of our u, at the point 0, 2. Again, we see that this parabola happens to be symmetric about the y-axis. And it appears to once again have the exact same shape as y equals x squared, but this graph appears to be exactly 2 units higher, and again, let's use that graphing calculator software to show that that's exactly what's happened. Once again, we've got a blue graph and a red graph. The blue graph is the graph of y equals x squared. Even if you can't see it, it's right there behind the red graph, because of course the red graph is exactly the same thing right now, y minus 0 equals x squared. But let's see what happens when we change this to a y minus 2 equals x squared. And just as we suspected, replacing the y with a y minus 2 had the effect of moving our graph up 2 units. Alright, let's try another one. Now let's graph all the ordered pairs for y equals the quantity x minus 5 squared. Now, of course, the only difference between this and our baseline y equals x squared is that we replaced the x with an x minus 5. Now, we are already in y equals form, so it is time for us to find some ordered pairs. But this time, note that if we let x equal 0, 0 minus 5 squared, that's going to be 25. And that is already off our set of axes. So starting our inputs at 0 and branching out from there is not a good idea. So the question is, what x values can we use to make sure that x minus 5 doesn't get too big? Because if x minus 5 is too big, then x minus 5 squared is going to be off the graph. So what value of x is going to make x minus 5 squared the smallest? Well, I think if x were 5, 5 minus 5 is 0, and that squared is of course 0. So instead of centering our inputs at 0, let's center our inputs at x equals 5 and branch out to the right and left of 5 and piece together our graph. Again, I'm going to let you create the ordered pairs now, graph them, connect them, find the x and y intercepts, and then we'll reconvene. Now, one of the first things we notice is that the y-intercept is not in the visual part of this graph that we can see right now. And if that's the case, in order to find our y-intercept, let's use the equation. And remember, the y-intercept happens when x equals 0. So let's just substitute in 0 for x and see what we get for y. So in this case, we'd say our y-intercept is 25, which is obviously off the graph. All right, and if we look at our graph again, it seems to be symmetric again. It's another parabola, it's another u, but it's not symmetric about the y-axis. It's not symmetric where x equals 0. It's symmetric where x equals 5. And it appears that we have the exact same graph as y equals x squared, but shifted to the right by 5 units. And let's use that graphing calculator to show that that's exactly what's happened. All right, once again, we've got a red and blue graph right on top of one another. The blue graph is y equals x squared, and the red graph right now is the exact same thing, y equals x minus 0, quantity squared. But let's see what happens when we replace this x with an x minus 5. Just as we suspected with our hand-drawn graph, replacing the x with an x minus 5 had the effect of shifting our graph to the right 5 units. All right, let's graph all the ordered pairs for y equals the quantity x plus 7 squared. Again, the only difference between this equation and our original y equals x squared is that we've replaced the x with an x plus 7. So let's see what effect that has on our graph. We are already in y equals form, so we're ready to find some ordered pairs. But again, we need to be really careful, because if we substitute in a 0 for x, 0 plus 7 squared is 49, and that's already going to be way off the graph. So we need to find values of x that are going to make x plus 7 significantly small, so that x plus 7 squared will still be on our graph. Well, if we substitute x with negative 7 plus 7 is 0, and that squared is of course 0. So let's center our inputs around negative 7 and go to the left and right of negative 7 to find our ordered pairs. So why don't you do that, find the ordered pairs, sketch the graph, connect them, find the x and y intercepts, and then we'll reconvene. Once again, we immediately see that our y-intercept is going to be way off the graph, so we had to go and find the y-intercept algebraically by substituting x equals 0 into our original equation. We get another nice U-shaped parabola graph, and this one is again symmetric, not about the y-axis, not where x equals 0, but where x equals negative 7. And it appears that it has the exact same shape as y equals x squared, but of course this time shifted 7 units to the left, and that is exactly what's happened. Replacing the x with an x plus 7 in this equation had the effect of shifting our graph 7 units to the left. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.